Hello everyone, my name is Aritro. I'm a PhD candidate at UMass Amherst, and this is a joint work with Andrew Land from UMass Amherst also. I'm excited to share with you our work on contrastive initialization scheme to improve model robustness under level noise. So I'll start with a simple example of learning with noisy levels. So in practice, we may have access to a noisy datasets where the samples are incorrectly labeled for some reason. Now, a common paradigm in machine learning is empirical risk minimization framework, where we minimize some kind of risk with a loss function, which is most often the cross entropy loss. Now, as a recap, cross entropy loss is sensitive to level noise. So I'm going to use this image example throughout the presentation, where the true level is bird, but it has been annotated as dog. And I'm going to analyze what happens when you pass this noisy sample through different models. So if we give these noisy examples to a CNN classifier with cross entropy loss, what is going to happen is that although the model correctly classifies it as a bird, because it has been incorrectly labeled, it will still incur a high loss value. Okay, and in the backward pass, it will still get a large gradient, which is obviously the wrong direction in this case. So for reference point, if we optimize cross entropy loss on C4 datasets under 90% symmetric level noise, cross entropy loss performs worse than divide mix by 40% and 70%. So divide mix is one of the state-of-the-art model. Actually, there has been many other new recent methods, but it will be in the similar ballpark. So what I want to emphasize is that large gradient part, which is actually challenging to tackle. I'll come to that part later, but let me start with a simple change in this training structure. So here I simply added a contrastive model initializer in the green part to initialize the CNN based deep classifier. So as a background, contrastive model is a self-supervised learning framework which has been found to extract really good representation on image datasets. Okay, so if we give the same noisy samples to the CNN classifier, we'll still incur high loss and we'll still get the large gradient direction. But in reality, if you learn this model with contrastive initializer, your model will perform better than divide mix by 10% and 70% on the same exact data sets under 90% symmetric level noise. So the point is not that we should use cross entropy loss when learning with noisy levels. Instead, we want to explore reason behind this observation and lay out possible approaches that we think can make this even better. So there are many paradigms for learning with level noise. I'll pick only two categories. These methods can be called supervised methods, and the reason will be clear when I compare them with semi-supervised based methods. So one of the way to achieve model robustness is to replace the cross entropy loss with some kind of robust loss function. For example, MA loss, generalized cross entropy loss, have been found to be theoretically robust to level noise. So when we pass the same noisy sample to the CNN classifier, we'll still get high loss value, and counterintuitively, it will actually pass small gradients. So the reason is that these loss functions are mostly non-convex, and in the high loss regime, they will saturate and pass small gradients. And that is one of the reason you get some kind of robustness guarantees. But it also comes with a different challenge. So these small gradients on high loss samples, those are corrects, can make them difficult to learn a deep CNN classifier. So the next idea is that you still want to minimize cross entropy loss, but somehow lower the weight for the noisy samples. So for this, a common heuristic is that samples that have higher loss value are more likely to be noisy sample. So this idea has been there for at least like 20 years, and it gained a lot of attraction in recent years. And it has been used in many other paradigms also for learning under level noise, including some semi-supervised methods. So the basic idea is that we can assign small weights to high loss samples and optimize the weighted risk with cross entropy loss. So instead of assigning some heuristic based weight, a more principled way is to learn a mapping from the loss value to the weight and learn that weighting network in conjunction with the CNN based classifier in an end-to-end manner. So this can be formulated as a bi-level optimization problem, and meta learning based optimization framework has been really useful for solving this kind of methods. So what I want to point out is that the noisy sample still has high loss value when you pass through the cross entropy loss layer, um, and the large gradient direction. But when you multiply with the small weight, it will pass small gradients for this noisy sample. Okay, so what is going on these two methods? So the general recipe is that we pass small gradients for these noisy samples, and this is similar to like removing these noisy samples. For example, so if you have 90% noisy samples, we would expect the model to remove those 90% samples and learn from rest of the 10% of the probably correct samples. So this is good as we want to do that, and these supervised methods works well across different data modalities such as image, text, and so on. And in limit, we would expect these methods to extract the correct classifier. But in reality, the number of sample is limited, and even so with the increasing model size. So the common wisdom that we have is that if we have a large enough data set, CNN based classifier can extract good visual representation in a purely supervised way, and there is no need to initialize with some kind of unsupervised representation learning model. But once we have a small enough data set, we probably do need to initialize with some kind of representation learning module. So essentially what I'm trying to say is that when you try to optimize with noisy levels, we are training a deep classifier with a much smaller data sets, and that can make the classifier difficult to learn visual representation in a purely supervised manner. So here is one common way to overcome this representation learning problem when you have noisy levels. So the idea is that you can use semi-supervised methods to exploit the noisy unlabeled samples in addition to the samples where we are confident that they are correct. So this idea has been used in many state-of-the-art methods such as divide mix. There are many tricks in SSL like consistency regulation, entropy minimization, level guessing method. I'll not go through them. But the general idea is that if we have two diverging models, they can guide each other and exploit even the noisy samples. So what I want to point out in this slide is that when we pass a noisy sample to say classifier 1, in the best case, we would hope that the second classifier would be able to correct the sample and get a correct loss value and the correct gradient directions. In other case, we would at least hope that the second classifier is not confident enough. So we can still use all the SSL tricks to learn at least some good representation. And that brings us to the central question we study in this paper. So we conjecture that SSL methods for noisy levels such as divide mix perform better than like supervised robust method due to their improved representation learning capability. So suppose all that SSL method brings is improved representation learning capability, there is no need to throw away those early supervised robust methods. In fact, we can study many other alternatives also for providing the improved representation learning capability. So one of the simplest solution is to just initialize the CNN with a contrastive model initializer such as SimClear. For image datasets, contrastive models are powerful for extracting good visual features, and they do not require any labels. So if we can provide a good visual representation, the hope would be that these supervised robust methods can only focus on the task of learning with label noise. So I'll discuss later why this decoupling can be a good idea in practice. I should also point out that in our paper we used SimClear, but there are many other new recent methods for learning representation in a contrastive framework, and we believe that those can be also really good. Okay, so I should also point out that the idea of initializing with a good representation learning model is not new. Even in the noisy level research, um, pre-trained ImageNet initializer is used in many vision tasks, and they have been also used for noisy levels. So they perform well in practice, and for detailed comparison, I would say check our paper. So what we have discovered is that under symmetric level noise, contrastive initialization performs better than the pre-trained initializer. And on asymmetric level noise, those pre-trained ImageNet initializer works well on the CIFAR datasets. But I think more strategy is required for the ImageNet initializer because CIFAR and ImageNet, they have a lot of class overlaps, increasing this confidence. So probably if you have a very dissimilar datasets than ImageNet, you would be better off with a contrastive model. The good thing about simpler model is that you do not need any other clean large scale similar datasets, and you can use the same dataset as the noisy level problem. So coming to the experimental result, this is the plot for different methods under 80% symmetric noise on CIFAR datasets. The LQ loss is the generalized cross entropy loss, and MWNet is the meta weight network, which is a reweighting based network in a meta learning framework. And CC is the categorical cross entropy loss. So here in both data sets, CC generalized cross entropy loss and meta weight net do not perform well when they are initialized randomly. But the performance improves significantly when you initialize with a simpler model. For example, optimizing cross entropy loss improves performance by 50% and 200% on C410 and C400 datasets. Also, meta weight net with the simpler initializer beats divide mix performance on C400 datasets and becomes much closer to the divide mix performance on the C410 datasets. And here is the same plot under 90% symmetric level noise. I do not have the result for generalized cross entropy loss with random initializer, but I got lower numbers than meta weight network with some initial experiment. So in this plot under high level noise, that is 90%, the CC loss, the generalized cross entropy loss, and meta weight, and all three bits divide mix with the contrastive model initializer, and the gain is more prominent. And here is a plot for 40% asymmetric noise on CIFAR datasets. Meta weight net with simpler initializer does beat ELR, which is another method, early learning regularization on C410 datasets, but not on the C400 datasets. We think more studies are required for asymmetric noise. Regardless, we do observe improvement for all methods in with the contrastive initializer. And here is the plot on real world clothing 1 million dataset. So cross entropy loss with the contrastive initializer improves performance significantly than the CC loss with the ImageNet initializer. However, here cross entropy loss with the simpler initializer do not beat divide mix performance, but it brings the number much closer to the SOTA number. So to conclude, we have shown that many of the supervised robust methods do not learn anything useful under high level noise rates. However, they perform significantly better with the simpler initializer on image datasets and can even outperform previous state-of-the-art methods for learning under level noise. Even the typical methods that you use, like training a deep neural network-based classifier under categorical cross entropy loss, can outperform previous state-of-the-art method under some noise condition. So this observation suggests that lack of good visual representation is a possible reason that many supervised methods perform poorly on image classification tasks. So we believe that cross entropy loss with the simpler initializer can serve as a strong baseline in future research in level noise. Next, as I was alluding you to the next point, We believe that decoupling the representation learning problem from the problem of learning under level noise can be beneficial. So imagine you are learning a new model which is not SSL based, and it does not perform well on imagery assets under level noise. So you cannot be sure whether it's because of the representation learning problem, or is it that your model actually is bad under level noise. So we believe that although SSL methods perform well, this decoupling can lead to more powerful, robust methods um, that can perform well across different data types, and not necessarily on image where there is a standard way to learn representation in a unsupervised or semi-supervised way. So with that, I will end my presentation. Thank you for your interest in our paper. For details, please check our paper, and the GitHub page also contains the code to reproduce and all the pre-trained contrastive models. Thank you. Bye.